Hello, John here. Welcome to another PyProx tutorial helping you understand the impact of uncertainty in data and simulation. In the next few minutes I'm going to teach you how to use Approximate control Variate Monte Carlo, ACV for short, to compute multiple statistics of vector-valued functions. This tutorial will build upon previous videos that showed you how to build ACV estimators for scalar value functions and how to construct single fidelity estimators of multiple outputs. In a previous video I showed you how to compute a statistic Q0 of a scalar high fidelity function f0 using M low fidelity models, where all models map a d-dimensional random variable z to a scalar. The form of a scalar ACV estimator is given on this slide. It is a weighted correction of a high fidelity Monte Carlo estimator computed using a set of samples z0. The control variate weights eta are a vector of length m, and each of the m corrections consists of two low fidelity MC estimators computed using different sample sets zm and zm star, where I'm referring to corrections by the notation delta. We can still use the vector form of the ACV estimator in the top left to construct multi-output ACV estimators, but we have to redefine a few terms. First, let's consider the estimation of a single statistic of a vector value function. In this case, model fm now maps the random variable z to a vector of s outputs, and the estimator produces a vector of statistics also of length s. The definition of eta and delta must also change. Eta becomes a matrix of size ms times m, and delta becomes a long vector of size ms. The matrix eta is shown on the left, and the vector delta is shown on the right. The terms in the blue box represent the differences of the first model two estimates of each of the s statistics. Similarly, the terms in the green represent the difference in statistics computed at the nth model. This general case naturally collapses to recover the scalar ACV case when s equals 1. ACV estimators can also be used to estimate multiple statistics of a vector value function. For example, on this slide I give an example of how to compute the mean and covariance of the high fidelity model. To handle vector and matrix statistics such as mean and variance consistently, we must always flatten matrices into a vector. This is done by the flat operation that concatenates each row of a vector into one long vector of length s squared. For our example, this vector is appended to the end of the mean vector. So now the ACV estimator is a matrix of size L equals s plus s squared. We again must change the sizes of eta and delta. Eta becomes a matrix ml times L, and delta becomes a vector of size ml. The vector delta is expanded on the right. The terms in the blue box represent the differences of the two mean estimators computing using the first model. The red box represents the difference between the two covariance estimators also computed using the first model. This decomposition carries on until we fill delta with the difference between two covariance estimators computed using the last model, which are highlighted in green. A multi-output estimator is unbiased, just like scalar ACV estimators, but now the variance of the estimator is actually a covariance matrix. The expression of the optimal covariance matrix shown on this slide is found by using the optimal control variate weights that minimize the determinant of the covariance matrix. A 5-step procedure can be used to construct multi-output ACV estimators. The first step executes a pilot study to compute the necessary quantities needed to minimize the estimated covariance. The second step optimizes the number of samples, nm, to minimize the determinant of the ACV estimated covariance. Step 3 randomly generates n plus 1 sets of input samples p0 through pm of sizes p0 through pm. Step 4 evaluates each model on the necessary samples and stores all s outputs. And step 5 evaluates the estimator. This procedure is very similar to that used for scalar ACV, other than the fact that we're dealing with s outputs for each model, and that the variance of the estimator is now a covariance matrix. As I showed earlier, the covariance of an ACV estimator takes the following form shown on the top of this slide. We can compute the terms of this covariance matrix using the two expressions on the bottom of the slide. In the next few slides, I'll derive exact forms for these two expressions when estimating vector value means, covariance matrices, and both simultaneously. I will go over the expressions pretty quickly, but feel free to pause the video to take a closer look. My main reason for including these slides is just so that you will be able to have a place to look up these formulas whenever you need them. So first consider the estimation of a vector value mean. The delta covariance matrix of two models m and n using their respective samples z and z star is a scalar multiple of the model covariance. Similarly, the covariance between q0 and delta is a scalar multiple of the covariance vector between model 0 and model n. The scales in question depend on the size of each sample z and z star of each model and the size of their intersection. The exact formulas are shown on the bottom of this slide. This slide presents the estimated covariance formulas when estimating a covariance matrix. The estimated covariances are the weighted sum of two matrices Wmn and Vmn. You can find the formulas for these matrices in my tutorial on multi-output single-fidelity Monte Carlo estimators. The weights are given on the bottom of the slide. Finally, this slide presents the formulas for estimating the mean and covariance together. The relevant covariances are now block matrices. Consider the delta covariance as an example. The upper diagonal block is the delta covariance for mean estimators. The lower block is the delta covariance for covariance estimators. Similarly for the covariance between Q0 and delta. We already discussed the form of these diagonal blocks, so look back through this video to find the exact expressions. What remains is to compute the off-diagonal blocks. These are just scalar multiples of the matrix B that was given in my video on multi-output single-fidelity Monte Carlo estimate. Just as we must do for scalar ACV estimators, practical use of multi-output estimators requires optimizing the vector partition sizes of an estimator. In the figure, I visually depict the partitions and their sizes for a 3-model ACVMF estimator. However, I won't go into this figure again because I've spoken to it many times in other videos. ACV estimators of multiple statistics can be computed on each statistic of each model independently, but games must be played to determine how to optimally allocate samples to each model. For example, do we take the optimal partition sizes associated with the statistic and model output that has the largest variance reduction relative to the single fidelity Monte Carlo estimator of the same form? Or do we use the allocation associated with the worst variance reduction? Using the expressions we just covered, we no longer have to make this subjective choice. Instead, we can just minimize a scalar metric that is a function of the estimated covariance. Because the optimal control vary ways are derived by minimizing the determinant of the covariance, this metric should also be used when determining the optimal sizes of the estimated partitions. Consequently, we optimize multi-output ACV estimators using the optimization problem on the slide. This optimization problem reduces to the optimization problem that was presented for scalar ACV, that is, when the number of outputs S is equal to 1. On this slide, I compare these two approaches for computing the mean of a high-fidelity model with 3 outputs. The covariance between the models and their outputs is shown on this slide. Specifically, I compare a multi-output ACV estimator that uses the outputs of all models to reduce the determinant of the estimated covariance with the ACV estimator that uses one output from each model. The bar plot on the right depicts the variance reduction of the output 0 of model 0 using these two approaches. The variance of the multi-output ACV estimator labeled MOACV is almost 2 orders of magnitude smaller than the single output ACV estimator labeled SOACV. That brings me to the end of yet another PyProx tutorial. Hopefully you now understand 3 things. 1. How to use ACV estimators to approximate multiple statistics of vectored value functions. 2. That the estimated variance is still the best way to quantify the quality of multi-output estimators. However, unlike scalar ACV estimation, the variance of multi-output estimators in general are matrix. And 3. Because the estimator covariance is a matrix, we must find the optimal multi-output estimators by minimizing the determinant of the estimated covariance. See you next time.